Sorry, yeah,
I've been prepping.
There's AP class questions, or can we go over those, or still?
Well, let's look at where we're at here. Hold on one second. Let's see. We have 2 people who have not submitted AP questions for Ben and Ava. And then that's for Unit 5. Same 2 for Unit 4. Let's try next class. I know, I hate to do it. But I'd like, to give people a chance to, do it, Piercy.
Did you do 17 from 6-5?
6-5, 17.
No, I'm just here tomorrow. What? Oh, that's way worse. So I will be quite from tomorrow, Saturday.
All right, let's see here.
It's over.
All right. It says a leaky 10-kilogram bucket is lifted from the ground to a height of 12 meters at a constant speed with a rope that weighs did you say 17 or 16?
Yeah, 17.
Okay. Did I sign 17? Okay. I don't remember anymore. We'll double check here. I definitely did not assign 16 or 17.
Wait, could you go over the models?
This is what I have written down.
Oh, I definitely like to write down 9.
That's 6-4? Oh, 6-5 is that. Oh, 6-5 is the. Okay.
Let's explore. I don't want to take all. Let's explore our options, buddy.
Sorry, I was looking at the wrong stuff entirely. Okay, I'm on it, Pierce. This is not the question.
I was going to say, it doesn't really seem very related.
No, I was just thinking it would have to be a work problem. This is the problem, right?
Yeah.
Okay. Okay. In a certain city, the temperature in Fahrenheit T hours after 9 a.m. was modeled by the function T of T equals 50 plus 14 sine pi T over 12. Find the average temperature from the period of 9 a.m. to 9 p.m. So I'm going to say 9 a.m. since T is the hours after 9 a.m. 9 a.m. would be T equals 0. And 9 p.m. would be T equals 12. So our T average should be 1 over 12 minus 0, integral from 0 to 12 of 50 plus 14 sine pi T over 12 dt. So you could type this into your calculator as it's currently written. If you want to do it by hand, we'd have 1 over 12 and then 50t plus 14. And then to do the integral of this stuff, I'm going to have to do a u sub. Where dt is going to be 12 over pi du. And the integral of sine is negative cosine. Plug my u back in. So 1/12, and then I have 50 times 12 plus 14. Well, we should say, let's make that minus. Man, that is a gassy pop. Times 12 over pi, cosine of 12 pi over 12. And let's see, cos 12 pi over 12 is just 12, or just pi, right? And cosine of pi is -1. So that's going to be 50 times 12 plus 14 times 12 over pi. Oops, and then we still have minus, 50 times 0 minus 12 times, or 14 times 12 over pi times cosine of 0. So let's see, that's 0. This is +1. So if I look, that guy and that guy are going to cancel out, right? So it should be 50, I think, then. 50 times 12 times 1 over 12. You guys buy that? I think that's right, Piercy. Let's look real quick. This was 6.5, number 17. Oh, boogers. What happened?
Does that cancel out? I don't think so. It's -1.
Well, it's minus a -1.
Yeah. And then
Oh, yeah, because this one would have been so there we go. Yep. So that would be plus 28 over pi. Or 28 pi over 12. Yeah. There you go. So there it is. And you could reduce that and turn it into decimal. I think it's about 59 is what the textbook says. Thanks, Braden. You knew something was fishy there. I made a little goofy on the minus sign, huh? It happens to the best of us sometimes, doesn't it? Classic. You happy?
Yeah.
Okay. I think the trickiest part was getting the bounds of integration right, is calling 9 a.m. 0 and 9 p.m. 12. Probably if you got that far, you could have calculated it out to the end at minimum, right? Who's next?
You do 11 from 7 foot.
Absolutely.
Absolutely.
No reason this can't be fun, guys.
What?
So reminder that what is going on? My OneNote's been really just like battling me today, and I haven't been happy with it. So if you remember, we do something similar to this, I thought. Yeah. So remember we did this one already, right?
Yeah.
Remember tan inverse is the same as arctan, right? So this is almost going to be the exact same problem, except instead of a x, I have a 4x or whatever.
Yeah.
But not, or for t. Yeah. But whatever. So if I do the derivative of tan inverse, that's going to be 1 over 1 plus 4t squared times the derivative of 4t. So du is going to equal 4 over 1 plus 16t squared dt. And then v is just going to equal t. So my integral of tan inverse 4t dt is going to equal u times v minus the integral of v du. Yep, t times tan t. So to integrate this piece, I'm going to think about that as like 4t over 1 plus 16t squared. So I'm going to do a u sub here, where u is going to be 1 plus 16t squared. So that means du is going to be equal to, well, I'll write it out. Probably most of us aren't super duper comfortable doing all the rearranging in our head, right? So I'll call that du over 8 equals 4t dt. So we have then the integral of, we have, what do we got? We got 1 over u, and then we have 1/8 out front and a du, right? Now we can do this. That's no problem. Oops. So that's going to be the natural log, the absolute value, and I'm going to put my u back in. Plus c. Now note, you could probably drop the absolute values here. Why can I drop the absolute values here? That thing is always positive, right? 1 plus something squared is always a positive number. So could drop the absolute value if you wanted to. Not wrong to leave it. But if the back of the book dropped it, that's why.
Why did you divide by 8 there? Sorry.
Well, I wanted to make, I want to make du equal to that. I wanted to replace that stuff. So if I divide both sides by 8 and then multiply by dt, I have 4 dt on that side. That's all I was trying to do, is just get that stuff to match over there. And if you did all of it, like if you divide by 32, it's fine. Like the 4 that's left in there and the 32 are just going to reduce and you're going to get the same thing. And just like me eliminating like a little bit of extra step for me of reducing. Not a big deal though. Does that feel good?
Yeah.
Pierce. 5 same section? Sure. What'd you pick for u here? I picked t. Because when I take the derivative of t, what do I get? Yeah. Because boom. Right? Now, to do the integral here, I have to do a u sub, right? And that's kind of stinky, but like, I'll get over it. Again, I did all these problems at one point before I picked them to assign, but it's been a minute. But that's my suspicion, is that I am going to want to so I did u times v minus v du. Notice that I brought the negative out front and made it positive. And look at this. We already did this, right? Oh, that's so convenient. And then it should just be cleanups from there. Does that feel okay, Pierce? So just some like, you know, simplifying or whatever, but I assume that's right. Yep. Oh, what'd I forget? Plus C. Ah! What a bungle that was. What do you guys think? It's all right. Again, the integration by parts should run relatively smoothly. You're not going to see any like too much stuff in here that's like, oh, that was a nightmare trying to piece this together because I had too much stuff. Eventually, like the hard ones, what ends up happening is we have like an integration by parts inside another integration by parts, where it's like, okay, this is my u and this is my dv, and then to integrate dv, I have to do another integration by parts. That can happen. Those are yuckarooskies. You don't have anything like that here. Yeah, Piercy.
Sorry, I'm just gonna.
It's okay.
How did you get you solved to get b?
Mm-hmm.
How did you get to the negative 1/3?
Because I have du over -3.
Oh.
So I just pulled that out front and then integrated, you know, e to the u, which is just e to the u,
Yeah.
and then put my u back in of -3t. Does that feel okay?
Yeah.
No problem. Again, that's why I try to tap dance a little bit after I finish one of these problems to make sure we have time to process.
You don't tap.
Yeah, just like, you know, just like vamping, riffing, you know, just like killing some time while people process what I just did. Because sometimes I go pretty fast, like faster than you guys can keep up with. I don't mean to do that. I just get excited and go.
Well, Mr. Colligan, if you cited today, we said that you were the, like, you have to give an example of someone who's intelligent, we picked you.
She picked you last year too.
Yeah.
Don't tell Mr. Oseki. Apparently we're fighting over who's the smartest person in the school. I
love you.
didn't know I was fighting with him, but apparently I am.
Yeah, just a second. You're not like a rat. That's so
So, I don't know.
Everyone said that you were very intelligent because you just know, like, so many subjects.
That's what he
There's a Great Gatsby. Someone was telling me how you, like, were talking about the Great Gatsby because they were reading it.
Yeah, we talk about books sometimes.
Do you like read for fun?
Mm-hmm.
What are you reading right now?
A Stephen King book called Duma Key.
Like, is it about Russia? With the lower house?
It's what?
Is it about the lower house of Russia?
No, it's about a island off the coast of Florida, like in the Florida Keys.
I was thinking the Russian lower house.
What's your favorite book you've read?
Oh, I don't know.
What's your favorite genre to read?
Do you like math? Like,
I read some like nonfiction stuff here and there, like that, but you know, like I read all kinds of stuff, but
Whatever you're doing in math.
all right. All right, let's move on then. Today we're going to do 2 sections. We're going to do 9.1 and 9.2. Shouldn't take the whole hour to do both of them. These are relatively straightforward ideas. And then you can have more Mr. Kulik question time.
Get to know me.
Yeah, sure, whatever you
Yeah,
want.
we should do like
Q&A.
All
icebreakers.
right. So section or chapter 9 is about differential equations. This is maybe one of the most applicable areas that you'll see in like your first semester calculus to the real world.
Just keep on going.
Well, to be honest with you, like chapters 5 and most of 6, we just developed integration. And now I'm just, rather than putting all the application stuff together and all the like the integration tricks together, I'm just like, here's some integration tricks and here's some application and we'll do a test. And then here's some more integration tricks and some more application and we'll do a test. You know what I mean? Like that's what I'm trying to do, is just so it's not all like the same thing. Because to some extent I'm trying to match up stuff that's like the hardest stuff with stuff that's not so hard, rather than put all hard stuff together.
Yeah, imagine
Like-
all applications on a test.
Yeah, like all application can be kind of overwhelming when you have just like, oh my God, this is like just calculus story problem after calculus story problem after calculus story problem. Versus like, okay, here's some story problems, and here's just some like normal symbol push. And here's some, more story problems, and here's some more just like symbol push. Like I when I broke the tests up for the second semester, I tried to do that. So 9 or chapter 7 is all like secondary integration techniques, right? So we have U sub, and then it's just like, okay, what if you can't use U sub? And now it's like trying to fill in some of those other integration techniques. And I start with the stuff that I feel like is just like a natural extension of U sub, like when we did the polynomial division or the partial fraction or the trig inverse stuff, because those are just like, you just got to do a little bit of algebraic massage and then it's a U sub problem. So I felt like that stuff, but integration by parts is completely different, right? Like that's a whole new technique. So that I wanted to stand alone and separate it from U sub so it's not confusing to see it as like 2 of them right back to back or whatever. I don't know. I'm just trying to build stuff together that makes, I think, a doable test that's still like sensibly constructed. Anyways, so differential equations are like one of probably the most applicable real life things that you'd see in calc. Because really any real world situation where something is changing and you can measure the change easily is something that you might want to write a differential equation to describe, to model. So one of the most obvious places is just talking about population. So if you have a population and you're looking to describe how that population is changing, you really have 2 variables. You have time and you have the population, right? So let's assume that we have exponential population growth. So we're just going to assume that population grows at a rate proportional to the size of the population, which probably isn't much of a stretch, right? If you have a lot of individuals, they're going to reproduce at a faster rate than if you have just a couple of individuals, because takes people to make people, right? The more people you got, the more people you can make. Everybody agree with that? Seems pretty sensible. So if we say that the population grows at a rate proportional to the size of the population, when we say something is proportional, it's just some constant times the variable, right? So we have dp dt, that's the rate of population growth, is K proportional times the population P. Right? Everybody's okay with how I got to that? Now we're going to make an assumption here that P is non-zero and P is positive. Why are we going to do that? Yeah, if it's a population of things, you can't have negative things. And if there's zero things, well, how's it gonna reproduce, right?
Nothing.
Yeah.
It's gonna happen.
Yeah, even if it's asexual reproduction, like in like a bacterium or something. If you don't have any of them, you can't even do that. And if you have one bacteria, you can still reproduce because it can do it asexually or whatever. AP Bio.
Dave class.
Mr. Coolman, you even know AP?
I should really like that class. Hot take.
So, assuming that this K is positive, then our rate of population change is going to be positive, right? Because we're assuming that P is greater than 0. So sure, then the derivative has to be greater than 0 because positive K times positive P is positive. Everybody cool? Okay. That implies that population is always increasing. And furthermore, as P increases, so does P prime or dp dt. Does that feel okay there? Yeah. Okay. Can you think of a function whose derivative is a constant multiple of itself? Yeah, well, let's really say e to the kx, because what's the derivative of that?
E to the kx.
K times e to the kx, right? The derivative is k times the original function, right? There's a function that's a derivative of itself. Pierce, does that make sense? Is kind of like what the verbiage is? It's usually easier just like once we say it, it's like, oh yeah, of course that's what that meant. But, okay. Now, if we consider all possible solutions to that differential equation, you're going to have infinitely many, right?
Yeah.
Because what do you really have when we integrate this? You get something like that, right? So because of the plus c, we have infinitely many of these things. But remember, population can only be positive, so guess what we're going to do to all that stuff? See you later. Discarded. All right. Now, under what conditions is this model going to be appropriate? Is population going to actually grow exponentially? Is that going to happen forever?
No.
No. What happens?
It like eventually dies down. Like
You run out of resources and the population dies down and it finds some carrying capacity, right?
yeah.
So either because you have a bigger population, you have more predators and those start taking a chunk out of your population, or you run out of space and there's no more room, or you run out of food or water or whatever. Something happens and you kind of reach a natural carrying capacity. So if we want, let's say that carrying capacity is going to be represented by M, cap M. So what we want is something that starts out growing exponentially and then kind of levels off. Does that kind of curve look familiar? Yeah, it's called a logistic curve. We talked about them last year in pre-calculus. So that's really what we want here. So remember, with a logistic curve, we have two asymptotes. You have an upper asymptote and a lower asymptote, where this is M and that's 0 or something. Everybody's okay there? Now, really what we want this to do is when our population is small, we want it to grow exponentially, right? But when our population is big, or even if it exceeds M, we want it to necessarily kind of come back down and start getting to m again. Everybody agree with that?
Is it because of the resources thing? Because of running out of resources and stuff, it has to plateau.
Right.
Okay.
Yep. So to do that, we're going to add in this factor 1 minus p over m. Now let's think about what that's going to do. If p is equal to 0, what happens in here?
It's gonna be 1.
It gets 1, and then p is 0, so the whole thing just becomes 0, because if you have 0 population, should it be growing at all? No. Okay. If p is less or between 0 and m, if p is between 0 and m, what is p over m? Less than 1, right? And 1 minus something less than 1 is positive.
Yeah.
So still having growth, right? Because you're still under the carrying capacity. Everybody agree? And the closer p is getting to m, the smaller this number is, so the slower it should be growing. Everybody agree? Because you're multiplying by a little tiny number, or a number very close to 0, I should say. If p is exactly m, what happens? This becomes 0, right? Which makes the whole thing 0, which means that once you get to m, you're never going to get past it because you stop growing. What happens if p is greater than m? So if p is greater than m, p over m is bigger than 1. 1 minus something bigger than 1 is negative, so you get that negative growth driving you back down to m. Everybody agree? Okay. These guys right here we call equilibrium solutions, because once p has reached that value, the rate of change is 0, right? dp dt becomes 0 for either of those situations, which means that once you hit that, you're never going to leave it. Because once you've hit a rate of change of 0, you can't go anywhere else, right? Yes.
How come PT equal is like equal to PT equals 0? I got it, but so is it because a positive number, how is a positive number gonna affect it?
I don't understand what you're asking.
Oh, sorry. How are these two equilibrium solutions?
Because if p is 0, the rate of change becomes 0, right?
Yeah.
So if population can't change, you're stuck at that population, right?
Okay.
So you're stuck at population of 0. If p is equal to m, this becomes 0, right?
Okay.
So the rate of change again is 0.
How does that become 0 though?
Well, because you have 1 minus m over m.
Oh, okay. It's a 1 minus.
Okay. And we talked about these things. So if we look, here's kind of our solutions now for this logistic model we just created. Notice that we've highlighted the equilibrium solutions. Everybody's okay there? So if our population was started out bigger than m, it's going to decrease until it gets to m and then hold steady. If our population is between 0 and m, it's going to increase till it gets to m and then hold steady. Everybody agree? Okay. Now, what we just did there, difficult. Modeling a differential equation is difficult. Will you be asked to do this on the AP exam?
No.
No. We'll ask you to do this. No. It's just a nice way of kind of showing you that this is something that happens in the real world all the time, that you may, like if you are a person in the real world trying to describe what's happening in the real world, this is mathematics that you would use quite frequently. So if you're interested in like designing medicines, frequently you'd start by modeling a differential equation of like how the bacteria reproduces and then how your medicine is going to disrupt that reproduction to try to like eliminate, or if you're looking at a pandemic and you're trying to design a vaccine so that eventually the pandemic dies out, you're going to start here with the mathematical model. If you're in business and you're trying to sell more or make more money, you're going to start with a mathematical model for your business. Like kind of anything where you're looking at things that change, we'd be starting with a differential equation kind of to create a model. All right. So let's look at some general, just kind of a general differential equation instead of like a super specific application. So we say differential equation is an equation that contains an unknown function and one or more of its derivatives. For example, y prime equals xy. Y prime's a derivative, and then one of the variables is the function y, and another one is some function x, right? We say that the order of the differential equation is the order of the highest derivative in the equation. So this guy would be a first order differential equation. If it was y prime equals xy, that would be a second order differential equation. Yay! Big deal, Mr. Kulik. I'm just talking about names. So we say that a function f is a solution for a differential equation if y equals f of x and the derivatives, if we substitute them in, it satisfies the equation. So like if y equals f of x is a solution to y prime equals xy, then the derivative of f should equal x times fx. Because I put the y equals f of x in for y. That's all this is saying. So to check that something is a solution, we're just going to kind of plug it back in and make sure it matches. We'll do an example here in a moment. To solve a differential equation, we're expected to find all the possible solutions. We've been doing this already though, right? Whenever we do an indefinite integral, what do we put at the end? Plus c, because how many functions could that possibly represent? Infinitely many, right? So if I have y prime is equal to x cubed, well, just y is equal to x to the 4th over 4 plus c, right? Same thing we've been doing. Just make sure we're putting plus c's at the end. Not a big deal. So let's look at a specific example here. So this says show that every member of the family of functions y equals 1 plus c e to the t over 1 minus c e to the t is a solution to the differential equation y prime equals 1/2 y squared minus 1. So what I'm going to start with is computing y prime. To compute y prime, what do I have to do?
Find the derivative.
Find the derivative. Great. What do I need to use to find the derivative of that y?
You use the quotient rule.
The quotient rule. Great. So how do I do the quotient rule?
Oh, it's been a long time.
I know.
Derivative of the top minus
It's
Derivative times bottom.
bottom times the derivative of the top. What's the derivative of the top?
CT.
C e to the t. Great. Minus the top times the derivative of the bottom, which is
Negative c.
Over the bottom square.
Good. Okay. Everybody feels okay?
Yes.
All right. Let's try to clean this up a little bit. So we'll do some of this stuff. Everybody's okay? Let's see what we get. We have c e to the t minus c squared e to the 2t plus c e to the t minus c squared e to the 2t over 1 minus c e to the t squared. Notice anything good that happened there? This should be plus here, huh? Right, because negative and negative. Oops, a daisy. Yeah. So what we really have is 2c e to the t. Everybody feel good there? All right. So that's my y prime. So I have 2c e to the t over 1 minus c e to the t squared equals 1/2 times y squared. But what is y? 1 plus c e to the t over 1 minus c e to the t squared minus 1.
Well, yeah, I should get that circle. Just plug it in.
Just plug y in, right? So far, so good?
Yes.
Okay. When I square a fraction, how do I do that?
You have to, like,
Square the top and square the bottom, right? And then this minus 1, to subtract that, I need to have a
common denominator.
common denominator. In this case, what would that common denominator be?
1 minus ct squared.
Mm-hmm. Everybody feel okay there?
Yes.
So I'm going to FOIL these two guys out and distribute that negative through and see what happens. Oops. What do you notice?
There's the
Mm-hmm. Anything else?
1.
Mm-hmm. And then if we multiply the 1/2 through, those guys would cancel out, right?
Wait, but 1 and 2 ct plus 2 ct be 4.
Or you can do it the way I just did it.
Oh, yeah, I get it. I'm sorry.
That's okay. And when you add those together, you get that, right? Which is exactly what we were supposed to get. That's a very difficult example of showing that something's a solution. The fraction made that pretty tedious. But notice, how much calculus did we really have to do there?
Not much.
Just had to do a derivative. That's it. And then plug stuff in and just do a bunch of crappy algebra, some tedious algebra, but like just algebra, right? Okay, so still using the same problem, it says find a solution to the differential equation y prime equals 1/2 y squared minus 1 that satisfies the initial condition y of 0 equals 2.
Do you find the integral?
No, we already have the general solution, right?
Oh, is that the initial equation?
So now all we're doing is plugging in the values for y and t to solve for c. What is e to the 0?
1.
1. So really this is that, right? How do I solve this for c now?
Cross multiplication.
Good.
And then you just like middle school algebra.
So C is 1/3. So we'd have y equals 1 plus 1/3 e to the t over 1 minus 1/3 e to the t. Do you think that's the way that the answer would look if this is a multiple choice question?
No.
No, why not? Think they'd have fractions inside of fractions?
Oh, yeah.
What would you do to get rid of the fraction inside a fraction? Yeah, we'll just multiply the top and bottom by 3, right? So probably the way it would look is that. What do you guys think? That's basically what you're going to be doing, is going to be solving for C with initial conditions and verifying that something is a solution. That's what your homework will look like. Not a lot to do. 3 through 13 odd. What's that, like 7 problems or something? Yes, sir.
How does that relate to the differential equation that it gave us?
Yeah.
Like, I'm confused why they even gave that. No, it said like y prime equals 1/2 y squared.
Because the solution, the general solution to that was this, right? So eventually, you're going to be finding this using calculus. We're not there yet, but eventually they're going to ask you to do that. It's not so bad. This one would have been quite hard because it's the type of differential equation that is not a lot. It wouldn't have been that bad. I take it back. I mean, it would have been kind of bad, but not like impossible bad. Okay. But we're not there yet. 9.2. We're going to talk about direction fields. The AP exam calls them slope fields instead of direction fields, just as a vocab piece. And Euler's method. We're not going to do Euler's method, though.
Yes, thank you, Mr. Taylor.
So let's say that we wanted to sketch the graph for the differential equation x or y prime is equal to x plus y. So the solution to that differential equation at any point xy, the slope of the solution at that point is just going to be the sum of the coordinates x plus y. So for example, at the point 0, 1, the slope should be 1. At the point 2, -2, the slope should be 0, right? You guys kind of get the idea? So if we do this kind of for all points, what we get is something called a slope field. So what this is like, if I did the point 1, 0, well, that gives me a slope of 1. So I draw a little line segment who looks like it has a slope of 1. I do that for all points. Now, or am I going to ask you to do this by hand? Almost certainly not, unless I give you like a really finite range. Like if I ask you to just use the lattice points between, like from x is equal to 1, 2, and 3, and y equal to 1, 2, and 3, or something like that, where it's just like, there's 9 points that I want you to deal with. Here I have a whole heap of points here. Like this would have been a nightmare to do by hand, because it's really tedious and time consuming. I have better things for you to do than like plug things in and draw little tiny line segments. Everybody's okay with that? Now, let's say we want to use the initial condition y of 0 is equal to 1. So that's like the point 0, 1, right? If I want to sketch the solution, I'm going to use the slope field to kind of draw my graph. So it kind of maybe looks like that. You guys buy that? I'm just kind of using the slope field to kind of trace through what that would look like. So I start with like, hey, there's my slope at 0, 1. The slope is 1. And I just kind of follow the slope field and I get something that looks like this. Look, what I drew is almost remarkably like what it actually is. Right? Is that a big deal?
You just like drawing around the line.
Yeah, I'm just following the slope field to kind of tell me how steep my line should be.
I don't know where to draw though. Like,
Well, it says the initial condition 0, 1. So I'm starting at 0, 1.
and then you're just making sure you don't touch any blue lines.
No, I'm just like, the slope there should be 1. When I get to here, the slope is flattening out, and then it's becoming negative. You know, I'm just kind of like following the slope curve, or the slope field. I'm not just using my eyes, you know, like I'm not really doing any calculation at all. It's just about like looking at the slope field and understanding what I'm seeing. Is that cool?
Yes.
Brayden, you got a question, or you just...
No, never mind.
Okay.
I realized that they were putting what the half works.
Yeah, they gave you a lot of slope field there. All right, so let's look at an example. Here it says to sketch the direction field, that means slope field, for the differential equation y prime equals x squared plus y squared minus 1. So this is me kind of showing the work that you'd have to do. This looks super annoying, right? Yeah, I'm not actually going to ask you to do that. Here it is. And we want to sketch the thing that passes through the origin. So there's my origin, right? So it looks to me like it's kind of doing one of these and then kind of doing one of those, right? I'm just kind of following the slope segments, telling me how to draw the thing. Cool? Will the AP ask you to do something like this? Sure would. Yeah, absolutely a question they would ask you to do. But how easy is this? This is like easy points, right? You just have to look at what you're... Yeah, but it's just like follow the paths, right? Could be a multiple choice. It could be a part of a free response question. I've seen that before. Slope field, they could. Sure. Yeah, I'm missing a piece in here. Okay. All right. Let's say that we have, nope. Let's say we have this differential equation that's based on Ohm's law. This is a physics thing with having to do with electricity. It's fine. It's not a big deal. No. This would be something that would be given to you, and I wouldn't even give you something that's like this physics-y.
Pierce, I don't think we need to know this in physics.
No, I just meant not the equation.
So, let's see. Inductance, that's L. Resistance, that's R. And energy, that's the voltage. So we'd have something like this. That's our differential equation. I'm just filling in the quantities for Ohm's law with the story problem. Now what I'd want to do is get di dt by itself. So I'd subtract the 12i over and then divide by 4. So di dt would equal 15 minus 3i. So what value of I would give me a slope of 0? 5, right? We would call that an equilibrium solution. So the values for the variables that make the slope 0 for all values of the other variable. So like there's no t here, right? But we'd be plotting this on like a ti axis. So when I is 5, regardless of what the t is, the slope should be 0 there, right? We'd call that an equilibrium solution. So if we wanted to sketch the slope field for this, or again, they're calling it a direction field, super annoying, would look like this, right? Notice our equilibrium solution right there at y equals, or I should say I equals 5. What is the slope at 5? All of them are flat, right? They all have 0 slopes. Identifying equilibrium solutions. This is something I would expect you to be able to do, as well as the AP expect you to do. Because what the AP is going to do is they're going to give you a slope field and then a bunch of differential equations to say which one, this is the slope field for which differential equation. Or go the reverse and give you a differential equation and then like 4 slope fields and go, which one of these slope fields matches this differential equation? So the way you need to do this is you need to be able to look at the equilibrium values and reason out which one matches, right? We'll do some more example of that in a moment. So notice this type of differential equation right here is di dt, but there's no variable t in it, right? We call this then an autonomous differential equation if, the variable which we differentiated with respect to, like t in this case, isn't actually a variable in the differential equation. And we're not doing any Euler method here. Enough of you. Da-da-da-da-da. Yep, I don't want to do that either. So let's do some examples from the homework here. I asked you to do 1 through 8 and then 19 through 23.
All with the directional method?
They're all just direction field problems, I believe. So let's take a look at number 1, part B, asking for the equilibrium values. What do you see?
1.5 and 0.5.
So you have to say the variable, though.
So y equal?
Y equals 1.5. Y equals 0.5. Do you see any others?
No, wait, no.
I see one more.
Oh,
Yeah, x equals 0.
Oh, wait.
it's like an illusion.
Oh.
Right, so you have to look vertically and horizontally, right? Everybody's okay with that? Fairly easy to do, right? That's all you need to do. We're just looking at it and identifying. Like kind of conceptual, but not so bad. Let's look at this one. Equilibrium values. What do you see? And probably 0, right? If you look at what's happening before, it is flattening out, right? What else do you notice, though? Yeah, I know I notice these vertical segments, right? So if I were to guess what differential equation might have this slope field, I would want stuff where if y is 0, 2, or 4, the thing becomes 0, and if it's 1 or 3, it would become undefined.
Oh.
Right? So if y is 0, then the slope is 0, right? If y is 2, the slope would be 0. If y is 4, the slope would be 0. If y is 1, the slope should be undefined. If y is 3, the slope should be undefined. That might be a potential differential equation that would have this slope field. You kind of see how I constructed that? Now, am I going to ask you to construct a differential equation from a slope field? No. Yes. But I would ask you from a list of differential equations which one matches the slope field.
Wait, Mr. Fuller, how could you tell 1 and 3 we're gonna result in no solution.
Look at the slope. It's vertical, right?
Oh, okay, got it.
Vertical slopes is where you have like a vertical asymptote.
How do you know how to put that in the denominator?
Because I remember with rational functions that I get a vertical slope when the denominator is 0 from way back. Now, it doesn't mean that it has to be this. It's just like a simple example.
Okay.
All right. Let's do a couple more. So here, we're given 4 differential equations and then 4 slope fields. We're going to pick out the slope field that matches each differential equation. To do this, I would start by writing down the equilibrium solutions for the differential equations. So let's look at number 3. What is the equilibrium values for number 3? But you got to give me a variable. Y equals 2. Great. Chanel?
May I go to the bathroom?
Yes. How about this next one? Y equals 2 and x equals 0. Everybody's okay? All right. And then let's look at 5 here. What are the equilibrium values for this? Well, if y equals 1, there aren't any. Excellent. Thank you, Pierce. Well, any value you pick for x won't make it 0, right? Because I still have y minus 1, right? How about this one? Sine x times sine y. Sine of 0 is 0. What else?
1 for x.
Pi, 2 pi, and then really like plus or minus, right? Because you could be going either direction. And because it's also sine y, you know, it's going to be the same there, right? All right, so let's look at our slope fields. So looking at letter I, what are equilibrium values? Y equals 2. Anything else?
Oh, wait.
No.
X equals 0.
Oh.
Which one did that match? Matched 4. Right down here. So that answer must match with I. Let's look at number 2. X equals 0. Y equals 0. And then look what's happening here.
It's just like go straight.
Yeah, it's right around 3. That's probably pi and negative pi. You know what? I have never been more excited for a pi day. So which one would this gone to? Yeah, that would have gone with 6, the sine x, sine y. All right. Let's look at this next one, number 3. What's our equilibrium values? Y equals 0, definitely not it, right? Look what's down here. That ain't flat. That's it. So that would have been with 1, or with number 3, right? So by process of elimination, this one should go with 5 is left. And 5 didn't have any equilibrium values. You see any equilibrium values here?
No.
That's great.
Good one.
Yeah, why is that diagonal going in there? If x and y are opposite coordinates, what will the slope be? It would be negative 1, right? If x is 1 and y is negative 1, the slope should be negative 1, right? So what are we saying? Like if we are 1 and negative 1, the slope looks like negative 1, right? So that's why we're seeing that diagonal going right down the middle. Do you guys feel okay on doing this?
That's fine.
Good. This is like This is the hardest thing in this section, is doing this stuff.
No way.
Yeah.
I could know that.
Yeah, I think the other thing was harder that we did.
This section, this is all we did in this section. Oh, yeah, I'm just saying in this section. That's the hardest thing you have to do is,
Oh, I thought you meant like at home. Like, really?
yeah.
That'd be a blessing.
So like, if you look at, I put in
Why, did she not like your class?
I put in my AP stuff,
Because your AP.
you know, like,
Also, I didn't.
look at all the slope field things that I have in here,
Score.
right? So like, should feel good about these sorts of things, right?
Yeah, those are.
Yeah, it'll be all right. So you have lots of slope field things to practice on in my AP also. Okay. Just FYI, I have the test format stuff in.
Oh, that's not bad. 5 MCQs, 7.
7 regular questions.
That's a lot. Only 2 FRQs, but that's scary though. That's so scary.
2 FRQs each
Why
part.
is there so much no count?
Well, again, so think about the no calc things. So it might be like integration by parts, right? That's not a tremendously time consuming, assuming you just have to do it once, right? You just have to know the formula. You know, like you might have to sketch a curve from a slope field.
Oh, but
Yeah, what's that take? Like 10 seconds.
that's just, is that the thing we do to
Yeah, you just use the initial condition and like we did it.
figure it out?
You just draw it in from the slope field. There's like almost nothing to do, right? And like,
Did anybody ask?
you know, like you might have to verify that something's a solution to a differential equation.
That's easy.
But that's, again, not too bad. In particular, if like it's not too complicated,
The only section I like so far.
right?
Yeah, for real.
Like, again, we have 7 questions because the things in there are relatively easy to do. So remember last class, I had told you that we should be able to finish our chapter 9 stuff this week. That feels realistic. And I know that some of you have a hectic week after trying to of other difficult class tests. I asked you to think about what you wanted to do as far as a test date. I asked first hour the same thing, and they floated this idea that I wanted to float to you guys and see what you thought. They thought doing half, like one part on Thursday next week, and the other part the following, whatever, Tuesday.
Will we know what
I
half
asked
we're
for that.
doing?
I would give you the no calculator half first and the calculator half second.
I'd love it.
I think it's not that bad.
Will we know which half, which sections are no calculator, which sections are?
That's true, yeah.
I don't care. I'll be in
Well,
Orlando.
I'm going all out next week.
The things that, you know, like a no calculator versus a calculator would be just like how nasty the integral is, right? If it's a nasty integral, like it's going to be in the calculator section because I expect you to just type in your calculator and press enter. If it's kind of straightforward and you're just using your antiderivative rules, then I would expect it to be in the calculator or the no calculator section. So really any of these sections could fall either place. It just depends on like how nasty the integration becomes. You know what I mean? Yes, Chanel?
Is it possible if I could take the second part in the testing room after school, like on Thursday?
Probably.
Okay.
Assuming there is a testing room after school because that's games day from Irish week.
Oh, okay, I have to ask, because I'd rather,
Yeah.
I'm so sorry, I'd rather just like get it over with
I
one day.
understand, and I'm amenable to that.
Yeah.
If you
I have a
did,
question.
then Joe
Yeah.
told me that one
You
person signed
said
up,
that.
so.
Wait, when's your off period?
5th hour
Okay, so.
tomorrow.
Well, yeah, BJ's. I have first hour study hall tomorrow. So,
They put me in pineapple.
You come.
I don't know what to do, because I won't be here next week anyway.
Don't laugh. Don't laugh.
You want to get something?
Don't you dare laugh.
Should I like
You want
take
something?
one half,
Don't laugh.
like
Don't.
Monday?
I think that makes the most sense.
And then,
Sign up for it.
and then maybe,
I'm not gonna lie.
it depends what days, would you do the other half Monday?
You could do the half that we did on. You could do the half we did on Thursday on Monday, and then take the other half with everybody on Tuesday. I think that's probably the easiest.
Oh wait, I have class Tuesday.
The week after Irish Week, yes.
Yes. Oh, okay. That's fine.
Because they have
So I'll
school
take it.
Monday, Tuesday, Wednesday.
Oh, so it's BAB.
It's an 8-inch apple.
It might be BAX,
Oh,
but I don't
okay.
even want to mess with the
That's fine. Because I'll
Wednesday.
take. Because
I haven't seen what the schedule is for that day yet. So.
yeah, because I get back home Sunday. So and I think I'm tutoring for 2 hours.
Okay.
So I think I could take it in the morning then.
Okay.
That 5th hour.
Yeah, you can
My
come in.
second
You can
yeah.
come in
I'm
my
gonna come
room,
in like early. Well,
Well,
not early, but like.
but you can take it in my room if you'd like. That's fine. Yeah, that's fine. I know you do.
Or Megan.
So that sounds like a good plan to me. Let's plan on that. If anything changes, let me know.
I don't think so. I just want to get it over with.
I would love for everybody to have it done before spring break, and you can go to spring break and just be like, I'm gonna get a tan and not worry about
Get
homework.
back to come back to get a
How you
tan.
do it?
Okay.
It's already been.
That is a
But yeah, okay, that sounds good.
Okay.
You usually find one.
Cool.
This-